Good morning, ladies. Today we're going to start by taking a look at percentage yield. For you to be able to calculate percentage yield, you need to know the difference between theoretical yield and actual yield. Theoretical yield is the maximum amount of product that is based on your calculation. So all the previous mole calculations that we've done, where you were given a certain amount of reactant and you had to work out how much product is going to form, that was a theoretical yield that you calculated. Actual yield is the amount of product that is really going to form. And we find that in most cases, actual yield is less than theoretical yield, and there are various reasons for that. Like, for example, the reactants aren't always pure, and there might be secondary reactions that happen as well. The formula that we use to calculate percentage yield looks like this. This formula does not appear on the data sheet, so you actually have to learn it. So percentage yield is equal to your actual yield, how much really formed, divided by your theoretical yield, how much you calculated was going to form, times 100. Let's look at the worked example on page 173. Calculate the percentage yield of steam obtained if 136 grams of steam is produced. So that is my actual yield. That is how much steam was produced. And they say that we use 20 grams of hydrogen gas and an excess of oxygen, which just means there was more than enough oxygen. So we have to calculate our theoretical yield by using the 20 grams of hydrogen. So to do this calculation, we need a balanced equation to start with. 2H2 plus oxygen react to form 2H2O. And they tell us that we've got 20 grams of hydrogen, but balancing an equation gives me a mole ratio. So my first step is to take the 20 grams and to calculate how many moles I've got. So number of moles is mass divided by molar mass. The mass is given as 20. The molar mass is for H2. So when I do this, I don't use that balancing number. I don't use that 2. I only use that in the next step. So 20 grams, the equivalent of 10 moles. My balanced equation, now I use the 2, tells me that 2 moles of hydrogen will produce 2 moles of H2O. But how much hydrogen have I got? I've got 10 moles. So 10 moles of H2O will form. And then we have to work out the mass of H2O, which is the number of moles, the 10 from there, times the molar mass, which I calculated over there, which gave me a mass of 180 grams. Now I can calculate the percentage yield because the actual yield was given as 136. The theoretical yield is what I calculated over there, times 100, and I get a percentage yield of 75.56%. On page 174 of your textbook, you'll find exercise 8.7, where you can go practice some of these percentage yield questions. Okay, the next thing that we need to look at is empirical formula and molecular formula. We did this last year as well, so hopefully you can still remember how this works, but let's take a look at it. Empirical formula is the smallest whole number ratio of the elements that make up a substance, and molecular formula is the true formula for that substance. Now, if you look on page 175 of your textbook, you'll see it says how to determine the empirical formula of a substance. So what I suggest you do is go work through that step by step and then attempt exercise 8.8 on your own. And then once you've done that, you can come back to the video because I'm going to go through the answers here with you now. So exercise 8.8 consists of 2 questions. Now, when I answered the first question, I wrote down each step. So I wrote down, I'm going to do this, and then I actually do it. But of course, when you answer this question in a test or exam, you don't have to tell me what you are going to do. You just answer the question. So the second question I did like that by just answering it like you would answer it in an exam. So how do I go about to do this? Now, the first thing I need to do, I need to find the percentage composition of the substance. So I've got 3 grams of substance, and I'm told 0.8 grams of that is carbon. So I work out the percentage carbon, 0.8 out of 3 times 100, and I get 26.67%. I do the same for oxygen, I do the same for hydrogen. Now I've got the percentage of each element in the compound, and we know that percentage means out of 100. So 26.67% means out of 100 grams, 26.67 is going to be carbon. And that is why my next step is to calculate the number of moles in 100 grams of that substance. So if I've got 100 grams, I'll have 26.67 grams carbon and so much oxygen and so much hydrogen and so on. So number of moles, mass divided by molar mass. I use the mass that I've now got, that I've got from my percentage calculations, divide by molar mass, which I get from the periodic table, and I get 2.22 moles of carbon. For oxygen, 71.1 divided by 16, and here you must just take a look. We are working out our number of moles using the element oxygen. So it's not oxygen gas, it's just oxygen, and that is why it is 16, which gives us 4.44 moles. And then for hydrogen, the same thing. The mass 2.23 divided by the relative atomic mass from the periodic table for hydrogen, which is 1, which gives us 2.23 moles. The next step is to write down the mole ratio, as we've just calculated. So carbon to oxygen to hydrogen will look like that. And then we have to determine the simplest mole ratio by dividing by the smallest number in the ratio. So the smallest number is the 2.22. I divide by that throughout, which gives me a 1 here, a 2 there, and a 1 there. And if I then have to write down the empirical formula, it's going to be 1 carbon, 2 hydrogens, and 2 oxygen, and 1 hydrogen. So CO2H. Then the second example, so percentage composition first. Out of 0.2525, I've got 0.06 grams carbon. So I calculated the percentage carbon. In the same way, I calculated the percentage hydrogen, and I calculated the percentage chlorine. And then if I had 100 grams of this substance, I'll have so many grams carbon, hydrogen, chlorine. So then I just need to calculate the number of moles. So number of moles, the mass divided by molar mass for carbon, for hydrogen, for chlorine. If I then write down the ratio, it looks like that. Divide by the smallest number gives me a carbon to hydrogen to chlorine ratio of 1 to 3 to 1. And finally, if I write down the empirical formula, it is going to look like that. Okay, exercise 8.9 on page 176. I also want to go through that with you. So there they ask us to determine the empirical formula, and they give us the molecular formula. So for glucose, they tell us that it's C6H12O6. The empirical formula is the simplest whole number ratio. So how can I simplify 6 to 12 to 6? By dividing by 6 and getting a 1 and a 2 and a 1, which gives me that empirical formula over there. 1.2, we have to do the same for carbon dioxide. So carbon to oxygen ratio is 1 to 2. I can't simplify that. So carbon dioxide's empirical formula is the same as its molecular formula. So it's possible that that can happen. And then 1.3, C2H2. To simplify that, I can divide by 2, which gives me CH. So that would be the empirical formula. And then for number 2, we've got C2H2. If I simplify that, like I did over there, I saw that the empirical formula is CH. Benzene has a molecular formula of C6H6. I can simplify that as well to get the empirical formula. And I also get CH. So that shows us that some substances might have different molecular formulas, true formulas, but exactly the same empirical formula when you simplify the molecular formula. Okay, let's take a look at the worked example on page 176. They give us the empirical formula as well as the molar mass, and they ask us to determine the molecular formula. Now, how do we do that? We work out the molar mass of the empirical formula. So molar mass for C2H5 is 12 plus 12, the 2 carbons, 5 times 1, the 5 hydrogens, which gives us 29 grams per mole. If I then take the molar mass that is given, divided by the molar mass that I calculated for the empirical formula, which is the 29, I get 58 given, divided by the 29 that I calculated, and that gives me 2. So that means if I've got the empirical formula and I want to determine the molecular formula, I must double everything. I must multiply everything by 2. So C2 becomes C4 because I need to double it. H5 becomes H10 because I need to double it. And that is then how I can calculate the molecular formula from the empirical formula if that molar mass is given. Right, so then on page 177, exercise 8.10, you can go and do that so that you can practice those questions. Thank you, guys.